Welcome back to Valiant PE. Today's topic, statics. Let's go. All right, we're going to recap from last time. What do we need to know about statics for this exam? The authors expect you to be an expert at it because it's a first or second year class. Because they expect you to be an expert, you're going to get a difficult question and it's going to make you think and may even have some tricky components to it, but it's not so crazy that you can't do it within 6 minutes. What type of question might we see? Well, machine design test, probably going to have some type of machine design component that's going to be a little bit weird. It's going to make you think about it for a moment. It's not going to be a simply supported beam. There you just need to find a reaction for. It's going to be multiple step solution where you're going to have some type of non-statics knowledge to solve the problem, like solving for a stress or using a safety factor, something like that. And you're not going to know that you're doing statics just by reading the problem. You're going to have to get into it. So the question wording can be confusing. How do you solve it? Do a really good free body diagram. Spend all your time here. You do this right, you're going to get the problem right. We can all do some of F and some of F and X, some of F and Y, some of moments, all that. Watch out for extra information that you don't need, Young's modulus, stuff like that. Watch out for answer options that aren't right. Because you're expected to be an expert, there's going to be one right answer, and then there's going to be at least one other solution as a choice. That's going to be really easy to get if you made a simple mistake. Divide by 2, forgot to use a radius instead of a diameter, or something like that. But if you do this right, you mitigate this problem. If you don't do a good free body diagram, watch out, okay? So we're not going to spend a lot of time on this. We're going to get straight into an example. Okay. Before we do anything, remember, we go through our pre-question ritual every time. This helps us reset after we just spent 6 minutes solving a problem. Let's first take a breath. Step 2, we're going to read the question slowly. A self-locking hook is suspended vertically by a strong chain. A strap is looped through the hook, and a force F is applied as shown. What is the maximum F the hook can handle if the yield stress of the hook pin is 36,000 psi? Assume uniform pressure distribution at the latch face. Here are my answer choices. And step 3, every time, what are we solving for? F and its units. This keeps us straight so we're not getting our units mixed up, solving for the wrong stuff. Okay, good. Let's breathe for a second and look at this. We have a diagram and a fairly confusing one. A self-locking hook is different from a normal hook in that the bottom half is pinned to the top half. When there's no load, this bottom half can swing freely. But when it gets under a load, it locks itself. So we've got an off-center pin here that's not in line with the load. So that's a little bit strange. Got a lot. Excuse me, you got a lot of dimensional information here and unique info about this pin. Good. So we've got some indicators. What's our first step that we're going to do is go straight into a free body diagram. Okay. Why did I choose the hook? Because this thing is made up of 3 components. You've got the thimble, or what I call the thimble. You've got the latch and the hook itself. I started with the hook simply because the force is applied to it. You could do it with a latch, it doesn't make a difference, but let's start out with a free body diagram. We've got a pin, so our pin reactions are Fy, Fx, excuse me, and we've got a uniformly distributed load here. And how do I know that? That's uniform. Assume uniform pressure distribution at the latch mating face, which is right here. Okay. Now, I'm going to rewrite this as a resultant right in the middle. I'm going to call that R. Okay, nothing else as far as reactions and forces go. So the first thing I'm going to do is write my first moment equation, or equilibrium equation. Sum of forces around point O, not 0. I'm calling that point O. That's my positive direction. I've got R dr minus F df. What is dr? Got some dimensional information here. Outer radius is 3, inner radius is 1.5 inches. So we're looking for, what's that middle radius there? Okay. Oh, excuse me, and our offset here is 1/2 inch. So this distance is the average of 3 and 1.5, which is 2.25. And we have to account for our offset, which is 1/2 inch. I account for that offset. So this distance, that's dr, that is 1.75 inches. df, that's easy. That's given, basically. This distance here, that is 0.5 inches. Okay, good. Let's write that. I'm going to rewrite that equation like this. And then I'm going to solve for r. F times df over dr. Let's put some numbers to it. 0.5 inches over 1.75 inches equals 0.286 f. So r, in terms of f, is 0.286 f. Let's draw our second equilibrium equation. Sum of our forces, that equals 0. Sorry. So forces in the y equals Fy positive minus r minus f equals 0. Let's rewrite that so that Fy equals r plus f. And let's plug in what we just solved for from r. 0.286 f plus f. Fy equals 1.286 f. Good. Now let's do our third equilibrium equation. Sum of forces in the x direction. That is Fx equals 0. Okay. What do we have here? Well, not much. We don't know what Fy is. We don't know what f is. And this equation doesn't really help us any, so we're a bit stuck. We need something else outside of our three equations to get us to the finish line here. So back to the problem. What do we have? Do we have any indicators here? We do. What is the maximum F the hook can handle if the yield stress of the hook pin, 36,000 psi? Okay, so that means what the yield stress of the material of this pin is 36,000 psi. Wow, I really butchered that. But this hook, or excuse me, this pin is in double shear. Or that's my assumption it's in double shear. It's at least in single shear, but I'm going to assume it's in double. So I'm going to come and write our generic shear stress formula. Tau equals V over A. How does that apply to our specific scenario here? Maximum shear stress is equal to Fy over 2 times our shear area. We're going to check this assumption at the end of the problem, but I think that's a safe assumption. Let's move on. So let's put some numbers to it. We don't know what this is yet. What's our shear area? Okay, what's our A? Well, they tell us the diameter is 1 inch, so that's pretty straightforward. Fy over 2. And I'm going to do pi over 4 d squared. D is 1. And I end up with maximum shear stress equals Fy over pi over 2. Now I'm going to leave it like this. I'm not going to reduce it right now. I'm just going to leave it like this for a second, and I'll show you why. Now, if you were to jump straight into plug 36,000 psi in here, that's wrong. 36,000 is the yield stress for an axial situation, not in shear. So we need to account for distortion energy criteria and reduce 36,000. So let's write it like this. We convert from axial to shear by multiplying our yield stress by 0.577. Okay, so this term is equal to maximum shear stress. And rewriting this equation, I'm just going to draw an arrow there. And let's solve for Fy. I'm going to move pi over 2 over, and we get 0.577, 36,000 psi times pi over 2 equals Fy. And we can solve for that. Fy equals 32,628 pounds force. Okay. We're still not done yet, though. We need to solve for F. Remember, we're solving for what is the maximum F? This guy. Okay. Let's come back to our sum of forces in the y direction equation and rewrite, or let's solve this guy right here. Just going to rewrite this. Sum of forces in the y equals Fy equals 1.286 F. I'm going to rewrite this equation again, do a lot of rewriting here. F is equal to, that's a 32,628 pounds force over 1.286 equals 25,372 pounds force. All right, did we get it right? Do we have that as an option? Let's check. Bam, we do. A. Okay, great. Now, here's how we can check that double shear assumption. If this pin were in single shear, the allowable F, the maximum F, would be half of the value I solved for. And since we don't have an option that's lower than this, double shear is fine. And that's it, guys. That's it. That's the problem. We've solved it. But what made this a PE-worthy problem? Well, we had a strange machine component. This hook is offset. When you load it up, it wants to rotate this direction to get force in line with the pin, but the latch is forcing it back, so you've got a strange device. So it makes you think for a second. We've got the shear stress component, and we had to come up with shear stress by knowing yield stress. So there's two more steps. So we had to come outside of statics with some other type of knowledge to complete the problem. And then you had to know that a uniformly distributed load, number one, that we had a uniformly distributed load, and two, that you could resolve it into a force right in the middle. So there are easily 3 or 4 different things you needed to know and assess quickly to solve this problem that are outside of the 3 equilibrium equations. So there's a lot to think about there. It's doable within 6 minutes, but you're not going to get that problem right in time if you haven't done this over and over and over and over again. That's the key to solving these problems, is just do examples over and over again so it becomes a rote memory. But that's it, guys. That's how we're going to do it. Remember, you don't have to be a genius to pass this exam. See you next time.